In the study of low-energy nuclear reactions, LENR, the significance of atomic hydrogen and deuterium cannot be understated. Detailed insights into electron interactions within these atomic configurations are essential for shaping a comprehensive LENR theoretical model. The scientific arena currently lacks a universally endorsed theory that clearly defines the mechanisms underpinning anomalous energy releases observed in LENR experimental setups. In spite of this absence, the field has witnessed the introduction of several hypotheses, each drawing upon distinct physical phenomena. While it's widely accepted that the ground state energy of a hydrogen atom is minus 13.6 eV, there's a burgeoning theoretical perspective suggesting even deeper energy states. This idea postulates that hydrogen atoms may possess energy states with a binding energy that goes beyond the conventional minus 13.6 eV benchmark. Experimental endeavors, notably those concentrating on hydrogen plasma, have documented the emergence of high-energy radiation, specifically gamma quanta with energies exceeding 300 keV. Such observations deviate from established expectations surrounding hydrogen atomic interactions. In response to these findings, a range of theoretical models has been advanced. A notable contribution to this discourse is the advent of the relativistic M2 equation. This equation, in its formulation and implications, provides a nuanced framework for analyzing hydrogen atoms and related ionic structures. Preliminary analyses anchored in the M2 equation suggest the possibility of identifying both traditional and novel high-energy states within the hydrogen atom's energy spectrum. The potential implications of these findings are vast. Verifiable empirical evidence underscoring the existence of these deeper energy states within hydrogen could signify a transformative development in the pursuit of sustainable energy solutions. Our journey begins with the relativistic M2 equation. By integrating the Coulomb potential energy and separating the variables, we derive the radial M2 equation, tailored specifically for hydrogen-like ions with a nuclear charge denoted as Z. We then transform this radial M2 equation using the Hartree atomic unit system. Now expressed in Hartree atomic units, the radial M2 equation is primed for further exploration. With the computational prowess of Wolfram Mathematica at our disposal, we tackle the task of solving this equation. The solution unfolds in the form of two linearly independent components. Our focus rests on the second component, intrinsically linked to the degenerate hypergeometric function of the second kind. We derive an equation from these insights that pinpoint the energy of hydrogen-like ions' ground and excited states. Using our foundational equation 5 as a base, we craft a concise and universal formula, represented by Formula 6. Given the condition of equal radial and orbital quantum numbers, this equation adeptly calculates the energy states of hydrogen-like series in Hartree atomic units, spanning both ground and excited states within the M2 equation's framework. Deepening our exploration, we observe the quantum number adhering to a specific series, incrementing methodically. When this quantum number is 0, Formula 6 seamlessly transitions to Formula 7, denoting the ground state's energy. In our computations, we account for the electron's rest energy. Keeping this in perspective, we present the binding energy formulas in electron volts, as portrayed by equations 8 and equations 9. A salient feature of the M2 equation is its ability to yield symmetrical solutions. However, our focus remains on positive energy values. For clarity, within these equations, C denotes the speed of light in Hartree atomic units, while Z indicates the charge of the nucleus in hydrogen-like ions. It merits emphasis that the solutions extrapolated from equation 8 and equation 9 align commendably with experimental findings. Moreover, to offer a visual representation of these discoveries, we've charted the normalized radial probability density, spotlighting both the ground state and the first excited state, as depicted in Figure 1. Now we're shifting our focus to the compact, deeply localized states of the hydrogen atom. When we map out the energy's dependence on the radial quantum number with orbital momentum according to equation 5, we discover intriguing results. Point 1 on this graph corresponds to a state with the familiar binding energy of minus 13.6 eV. However, point 2 unveils a deep compact state with a staggering binding energy of minus 479,790.38 eV. Further exploration reveals a pattern between quantum numbers and binding energies. This table showcases the binding energies as functions of quantum numbers. Intriguingly, states with both low and high binding energy share identical quantum numbers, which is a direct outcome of the nonlinearities observed in relativistic electron behaviors at elevated energies. Let's dive deeper into the compact state's structural properties. When we analyze the normalized radial probability density for state 2, it becomes evident that its radius is immensely compact, over 500 times smaller than a typical hydrogen atom. Such compactness offers effective shielding against the Coulomb barrier, thereby enhancing the likelihood of secondary nuclear reactions taking place. In our exploration, we transition to cylindrical coordinates. With non-standard quantum numbers in play, it's crucial to reinforce our analytical findings. Here, we introduce the M2 equation, in these coordinates, adhering to Hartree atomic units. To validate our solution, we tested its convergence at specific energy states. The results? A remarkable alignment at a distinct binding energy value. Figure 4, displayed now, showcases the radial probability density derived from our rigorous numerical analysis, all within Hartree atomic units. Building on the deep-state hydrogen atom theory, we envision a future with energy devices or reactors operating on a novel mechanism. Here's a step-by-step breakdown. 1. Molecular hydrogen is introduced into a catalyst-filled reactor. 2. The hydrogen transitions into its atomic form upon interacting with the catalyst. 3. We then excite these hydrogen atoms. 4. During this excitation, some atoms transition into a deep-bound state, emitting energy as gamma quanta. 5. Others move to lower states, releasing both gamma quanta and a typical low-energy spectrum. 6. These compact neutron-like hydrogen atoms can participate in secondary nuclear reactions. 7. We then harness this released energy using various methodologies. This is an emerging theory and calls for collaborative research across physics and differential equations for its validation. Thank you for joining us on this insightful journey. If you're keen to delve deeper into our research, do visit our website or simply scan the QR code on your screen. Your continued interest and support drive us to explore further and innovate. Until next time.